In this video, we'll integrate the function x squared plus y squared over the unit disk, which is the set of points consisting of x squared plus y squared less than or equal to 1. Let's first set up the problem in rectangular coordinates, although it's going to be difficult to compute it this way, so we won't carry out the calculation, but it's worth the time setting it up and then comparing to what will happen when we do it in polar coordinates, where it will be much more effectively computed. So the first thing I want to do is write it down as an iterated integral, and I've arbitrarily decided to integrate with respect to y first and then with respect to x. That means my x limits of integration will be constant values, and in fact on the unit circle as I move across the region, my x values start at -1 and end at x equal to 1. That tells me my limits of integration for x. I now fix a generic value of x, and that determines a vertical section of this region, and I enter at the bottom of the circle and I exit at the top of the circle. The curves where the y values are equal to the top and bottom I can get by solving my unit circle equation, x squared plus y squared equal to 1 for y, and the positive root will be the top of the circle, the negative root will be the bottom of the circle. And so that gives us our limits of integration for x. Again, you can calculate that, but it turns out to be a considerable amount of work to do that by hand, and we're going to do it in a much more effective way by using polar coordinates instead. So let's integrate in polar coordinates. The first thing I should do is to take my function x squared plus y squared and turn it into a function of the polar variables r and theta, and the sum of the squares of the coordinates are related according to the usual Pythagorean identity. X squared plus y squared is equal to r squared. So the function I'm integrating is just the radius squared. I want to take this integral now and integrate r squared over the unit disk. When I convert to polar coordinates, remember that we get an extra factor of r because that element of area should scale with the radius as well. So you're really going to be integrating r cubed here. And then we have dr d theta, so I should determine my limits for theta and then r. So let's do theta first. I'm going to think about theta equal to 0, and then I need to go all the way around the unit circle exactly once, so that means my range of thetas should go from 0 to 2 pi, and that determines my limits of integration. To see what happens for r, you should think about fixing a generic value of theta. So think of that as an angle here, just a generic one in the picture, nothing special about that one that I've drawn. And think about when you enter the region along the radius and exit the region along that radial direction. So imagine walking from the center, the pole, the origin, and walking along a radial line until you get out of the region. And what we see here is that the radius is 0 at the beginning, and then we exit at r equal to 1. And so my radius will go from 0 to 1, and that determines my limits of integration for the radius. Now it's simply a matter of calculation. I'm really integrating r cubed with respect to r and then theta, and this is a very straightforward calculation. We go up a degree and evaluate r between 0 and 1. We get a constant answer, and then I integrate with respect to theta and evaluate that between 0 and 2 pi, and a very straightforward calculation, I find that this double integral is in fact just pi over 2. If you have an opportunity, try doing it this way and compare. The polar form is exploiting the natural symmetries that this unit disk has and that this function has, and it's taking advantage of that to do things in a much more effective way.